Hi, I'm Ben-Yaakov. This presentation is entitled Differential Oscilloscope Probes, the Common and the Better. I'd like to thank Keysight Technology Company for permission to display in this presentation their oscilloscope captures that are using some of the probes that I'm going to discuss. There are some relevant videos in YouTube related to this subject. They are printed here, and I'm going to print them at the page of the YouTube video that you are now watching. And there is a disclaimer here that the probes shown or mentioned in this presentation are for educational purposes only. There is no endorsement or recommendation implied. So I'm referring now to, say, a half bridge. This could be a part of an inverter or a synchronous buck. And I'm showing here two differential probes. One, which is a must, because in this case we have this midpoint changing all over the place between 0 and actually the bus voltage. So you cannot use a single-ended probe, you have to use a differential probe. And then it's a good practice to use also a differential probe here, because there is a potential difference, always noise, spikes between the actual ground of the system and the oscilloscope ground. So this could be a good practice to do. So here is a shot, and this was obtained by Keysight Technologies. What I'm showing here as an introduction, I like just to concentrate on two plots, this yellow one and this light blue one. These are gate voltages. This is the low side here, and there is a high side gate. So this is the high side, taken by two probes, one A type, one manufacturer, and then B by another manufacturer, okay? So we see the low side here and the high side here. And now the probes were switched. That is, the low side now is probe B, and the high side is probe A. Now, let's have a look now at the low side. With probe A, we see this waveform, we see this oscillation here. With probe B, there's very little oscillation, and it's really damped quite a bit, but there is no question that this is much more cleaner than this one here. Now for the high side, here is the high side with probe B, here it is, the high side, and here is the high side with probe A. Again, probe B, much cleaner. There are no oscillation here, which are shown in the use of the probe A. So this is the subject matter of this presentation. Why is this difference, and what are these probes? And let's get started by considering what is a differential probe. A differential probe is built around a differential amplifier. This is a generic presentation. We have resistors and then capacitors. Some of these are parasitic, and then it turns out in order to get a flat response, you have to have the time constant of these to be equal. Only if the time constant are equal, you'll get a flat response. So therefore, if you have some parasitic capacitances, then usually there will be need for trimming. Same thing goes for the resistors. If the resistors do not comply with the requirement that the ratio here is like the ratio here, there will be a common mode signal at the low frequency. A mismatch in the capacitor will be a common mode error at the high frequency, and we are going to talk about it quite a bit. So we want these time constant to be equal for this response to be flat. So to get the desired response, we do have to keep this ratio as it's shown here, and then the gain will be Z2 over Z1, this over this, and usually this is going to be smaller than this, because if we want high voltage, we need to have actually here attenuation. So then the output will be A times V in when A is Z2 over Z1. And of course, we're going then to have a flat response, but we have a problem with the operational amplifier. If it is an ideal amplifier, it's going to be flat, but this is of course just impossible. So we have a limiting factor of the operational amplifier that has some finite response, and this will limit the bandwidth of this system. Okay? So in this case, we're going to see some impedance when we look at any of these inputs. And since we have these capacitors, then at very low frequency, we're going to see just the resistors. And as the frequency goes up, we're going to see actually just the capacitor, because the impedance of the capacitor will be lower than that of the resistor. So typically, this will be the input impedance, contrary for what we have the feeling that 1 mega ohm probe or 10 mega ohm probe, well, it's 1 mega ohm at low frequency, and this breakpoint could be at fairly low frequency, like 10 kilohertz or 50 kilohertz, and beyond that, the impedance goes down like minus 20 dB per decade, okay, like 1 over 2 pi, it should be F here, I'm sorry, should be going down like that. Now, as I've already mentioned, usually R2 will be smaller than R1, and therefore R4 will be smaller than R3, because usually we like to have the possibility to look at signals which are riding on high voltage, like in the case of the half bridge, and therefore we have to watch the voltage here in the amplifier, which is fed by some power supply, maybe 5 volt or 50, plus minus 15 volts, and the voltage that is seen in the input, it's about the same because there is a virtual zero between them. Then the voltage here is dependent on this voltage divider, which means that indeed R3 must be larger than R4, and this will also, of course, determine the transfer ratio, which typically will be attenuation. It'll be like 10 to 1, 50 or 100 to 1 attenuation here, which is for two purposes, and the main one being that you like to be able to cope with high voltage. Now, a very important test of a probe will be the common mode test. That is, for example, we can do it ourselves in a system. We can put these two tips together, put it to the midpoint, which is now switching back and forth between 0 and the bus, and watch the output. Now, if the probe is perfectly balanced, we shouldn't see anything. Well, never happens. We always will see something, and this is called the common mode rejection ratio of the probe. So what is it? It is a measure of how much of the common mode is penetrating to the output, and you can refer to the input or the output. The way I define it is as V out over A V common mode. A is the total gain here. So, for example, if we have a probe with a transfer ratio of 1 to 100, that is 100 to 1, in fact, that is a attenuation of 100, and let's assume that the common mode voltage here is 10 volt, and we see at the output 1 millivolt, then the common mode is minus 40 dB, okay? So this is not considered to be very good, because if the voltage here is 400 volt, then we are going to see 40 millivolt, which is quite a bit, okay? So common mode rejection ratio is very important, and it happens when this is not accurate. So therefore, you need trimming, usually for these. I'm not showing it, it's outside the scope of this presentation, but it is quite a bit of a tedious operation to match these as much as one can, because any deviation will cause a common mode error. And now we come to some commercial units. The first one that I'm showing here is a Keysight probe. This is a differential probe. And you can see that it has a end for the tips here, and then they can get these type of ends to grab the pins or wires or whatever. And then it has a control section here, and this is the B and C that go into the oscilloscope. Now here there are two wires, and then you can plug these heads to them. Okay. Another option is to add this probe, which is kind of spaced, and I guess you can get probably with different spaces. I'm not so sure. In any event, this is touching or supposed to be touching the circuit board at 2 points, and therefore the distance is small and the area is small. I'm going to talk about it a little bit later. And in this particular case, on this particular probe, we are talking about a 10-to-1, so it's for low voltage, it's only 40 volts, okay? It cannot cope, this particular one, this one is 60 volts, so it cannot cope with high voltages because of the fact that it is 10-to-1. And then it has a power supply, probably 15 volts, and here is the input impedance. The resistance is 100 kilo ohm per side, parallel to 2 picofarad. Well, it's not that hot. 100 kilo ohm, it will be loading some circuit. This could be very good for digital circuits, okay, for low impedance and low voltage, okay. So this is one example, and here is the performance. We see this is one model. Of course, they have many models. I'm not going to go over all the possibilities. The red one is often important. This is the V out over V in. So this is the response. And as we can see, it's up to, say, 200 megahertz flat. Okay, that's pretty nice. And then we have the common mode rejection ratio. So we start with DC, very good. It's a very good matching of the resistors, very good matching. By the way, I haven't mentioned that it could be only one section of an RC, it could be a number of sections. There are many ways to do it. I'm not going into it in this presentation, which is really not the major issue here. So we see better than minus 90 dB at very low frequency, but then it starts to corrupt, and at 1 megahertz it's minus 60 dB, which is also not too bad. It's 1000. Okay, so 1 volt of common mode will give you like 1 millivolt. 100 volt will be 100 millivolt. And here we see now the input impedance, and as I explained, it's flat up to a given point, and then we see the capacitor. An interesting plot here, not always given by manufacturer, is the maximum voltage allowed at any given frequency to any port, to any input. So at low frequency, you can expose the input to 40 volt up to a frequency of, this is 10 megahertz, so at 20, 30, up to 40 megahertz, you can expose it to the 40 volts. Beyond that, you have to derate, and you should not expose the probe to, say here, to a higher voltage than 10 volts. Why is this? Well, the reason is that at high frequency, the impedance is very low. I mean, relatively speaking, could be 100 ohm or hundreds of ohm. And then if the voltage will be high, you'll have a very high current. This will harm the components. So the current is actually limiting the voltage that you can expose the probe to at high frequency. I'm coming now to another probe. The nickname is Bumblebee, very well known. It's a 51 to 500 to 1 probe. It's switchable, okay? And the input impedance now is 5 megohm, quite a bit, and in parallel to 4 picofarad, which is not that hot because it's a fairly low frequency corner here. Of course, the differential input is twice this and half the capacitance. Now, the common mode rejection ratio is given here like a couple of points, and it starts 80 dB. It should be actually minus 80 dB. Well, that's a different way to define common mode rejection ratio, either minus or without a minus, but we understand that this is the ratio and the rejection of the signal, common mode signal. At 1 megahertz, it's 60 dB. let's compare it here. At 1 megahertz, it's 60 dB, so it's about the same. This is, however, a high voltage probe, of course. Because of this ratio, it can cope with hundreds of volts, okay? So this is a high voltage. Again, we see the unit itself, and then we have the two wires, and then we have the part which connects to the scope with the BNC. Now here we see the input impedance. Again, it's very typical. We see the 10 megaohm. This is the DC component, the resistor. And then because of this capacitor, with the other capacitor in series, we see the drop here, which goes to fairly low resistances or impedances at high frequency, as I've already mentioned. And here I'm showing another unit, another commercial unit. You might say it's a low end, certainly low cost, much less expensive than the probe I've shown earlier. It has this box here with the battery, of course, and then we have the probes and the connection to the BNC, and then we have different tips here for connection here. Here are two models. One is 50 and one is 100 megahertz bandwidth. Both of them are switchable between 50 to 1 and 500 to 1, okay? And therefore they can cope with 130 volt or 1300 volts respective of the attenuation, of course. And let's have a look now at the common mode rejection ratio. We see that at DC it's 80 dB. Usually you can see with the higher end probe that this number will be larger. But then at 100 kilohertz it's 60 and 1 megahertz it's only 50. Earlier we've seen 60 dB, so this is less susceptible to the common mode signal, 50 dB as compared to the 60 dB. The impedance is the 10 megohm in parallel to 1 picofarad. This is very, very nice. So this is another option. Of course, it has a somewhat lower performance, but it's also cost much less. And now I'm coming to another issue which is very important, and this is something I like to stress, and that is the fact that a probe with long leads has stray inductance. So this could have two effects. One, it may change the transfer function, and secondly, it may affect the circuit you are testing. But already we know that we are connecting the picofarad of the probe, whatever probe it is, and the megohms of the probe to the test point. But now we're also adding in series a inductance. For some cases, for devices with very high switching rates, like silicon carbide or gallium nitride, this might pose a problem. So this is a much better solution, if indeed it can be implemented. I haven't seen it on many units. I haven't seen it on the Bumblebee, but here Keysight gives you this option here, which is very nice. So what is the effect of this inductance? Okay, we have now an inductance at the input. To explore this, I prepared a simple LT-SPICE schematics. I'm showing here the two sides, one side, the other side, and then I'm combining them, multiplying it by 100 to get back the signal, because this is now, the resistance here is 4 meg, and this is 40K, so this is 100 to 1, and then I'm multiplying it by 100 to get the right value. I've added here a low pass, assuming that this is sort of representing the amplifier. This is about a few hundred megahertz, I don't remember exactly now. And then I've done some mismatching between the resistors. So this is 4 megohm and this is very slightly larger than that. And then also I've done the same thing with the capacitances. This is 1 picofarad, and I've changed this value from the correct one to 1.01. This is the correct one. This is 1.01. Everything is parameterized so that I can change things. So I've added here the inductances, and I've also added some coupling between the two wires, which is kind of makes sense because you have two wires going together. And then I have a AC and a transient sources, both sinusoidal and a pulse, so I can test various situations here of the probe. So first of all, we see here the small signal gain of this probe, which goes up to about 50 or 70 megahertz. Here we see the effect of the inductances, okay? The inductance plus the capacitance are causing here some oscillation. Now, obviously, it's outside the range, but if you have an input signal which happens to be in this range, few hundred megahertz, then you might have some disturbance and a gain which is not typical of this unit. So this could actually change the response in this area. Now, what about the input impedance? Well, it is like as we expected. In this case, we have about between, I'd say 30 kilohertz breakpoint, then it goes down as we have seen. So it here it's fairly low. This is, I'm sorry, in dB, should have been in ohms. And then I have the common mode rejection ratio, which in this case starts with 70 minus 70 dB because I've made the resistors very close. You can make resistors, these resistors indeed very close by trimming, and there are many ways to do it, by a pot, by laser trimming. There are many ways to do that. But at high frequency, you rely on the matching of capacitors, which are less accurate and stable. And here, so this is why I've made a larger error. And here it sort of comes to minus 40 dB at this frequency above 100 kilohertz due to the fact that I've added like 1% here. It's quite a bit. 1%, 40 dB, that makes sense. So then I've actually connected this probe to a half bridge. There are two transistors. These are silicon transistors. I've added parasitics to see some oscillations. And the probe is actually connected to the upper transistor. Okay, these are, this is now for testing the common mode. So here it is. Here are the two gates, gate 1 and gate 2. One is the lower one, and 2 is the upper one. This is gate 2, the upper one. And then I see here the output of the differential probe. And this is in the common mode. This is in this case that both of these are connected to the source. So we see here quite a bit. This is the 3 volt. Mind you, this is the 400 volt. So we have here a 400 volt pulse, and the remanence of it as the common mode is this error. This is the mid, point. So this is what I get as far as the differential probe with the common mode rejection ratio. Now, I'm connecting these to the gate, and again, I have some error here as before. This is for the low pass, and here it is now. This is now supposed to replicate gate 2. This is gate 2. And this is the output of the differential probe. Well, you see that there are quite a bit of errors here with this particular probe. Here we see the jump of the common mode also here. So it's sort of smearing out this phenomena here and this phenomena here. So we see that this probe is really not that hot, and you'd like to have something better than that in practice. And now I've added some inductance to the transistor, in order to enhance some oscillation and to see how the probe is coping with some high frequency oscillation. And here it is. You see that now I got this spike. This is due to the inductance at the gate and then oscillation of it. This is gate 2, okay? And this is the differential probe. Well, it's quite a bit of a difference here. First of all, it doesn't capture the very high spike and fast responding spike. There's no clamping here, but this is just the bandwidth. It's not enough for this sharp spike. And also you see that there's some extra oscillation, probably due to the fact that we have inductance at the input to the probe, okay? So we see that the probe can, of course, add errors in the measurement, and this is something to worry about. And here, this is an expanded scale. You see, this is the supposedly correct shape of the pulse here, and this is what you get from the probe due to the limited bandwidth and also the oscillation that it generates itself. Now I'm coming to, you might say, today, 2021, coming up 2022, to the top of the line in isolated differential probe. This is a Tektronix, which is using fiber optics for isolation. Okay, so this is the main unit. We have now a fiber optics, which at the end carries the differential amplifier. Okay, both the signal and the power to this differential amplifier are passed by the beam, the light beam. Okay, so there is no physical galvanic connection between this tip here, which has the amplifier, and the base here. So this is almost perfect isolation, okay? And the tip here then can connect, and I'll show some other option, to the circuit by these connectors, which are connecting the 2 points that you'd like to measure, and this goes into it and connect to these 2 points, while the amplifier is actually sitting here. This is one option. There are some other options, okay? So this has the best of the two worlds. Number one, very good isolation. And number two, no galvanic connection to ground and very little capacitance. Because what we have here, this is the tip, which is connected to the head. This is the amplifier. Here it goes fiber optics to the control unit. So what we are left with is some parasitic capacitances around the head here, around the head, okay? And if there is some current passing through this would actually cause common mode signal to be passed to the output. Like they are saying that this could be like 2 picofarad, depending on the location, etc. So this is the tip, this is the amplifier, and then it goes here. Now here we see another configuration of connection. The amplifier is sitting here, and here this is the tip, which now can actually connect to 2 spikes here on the board. So you have minimum area here and distance, and this is just as good as probably you can do today. So what is the performance? Well, not surprisingly, you can go to very high voltages here, the offset voltages, because of the very good isolation. We are talking about an amplifier after all. I mean, at the tip we have the amplifier, okay? So it's an amplifier, and it has the characteristic of an amplifier in terms of the input impedances and capacitance. There's nothing you can do much about that. But the common mode rejection ratio is, of course, very, very good. So it really depends on the head, on the capacitances, but you can see that at DC, where the capacitance is not affecting it, it's 160 dB. That's a lot. And if I'll go to 1 megahertz, which we compared earlier, it's really, again, depend on the tips, but it can be something like 145 dB, 110 dB. We were talking about 60 dB for the medium type differential probe. Okay, so there is no question that this is really, really much. Now, as far as the isolation, again, this is fiber optics, so you can go up to 40 kilovolt between the tip and the base. That is, the tip can be 40 kilovolt referred to ground, which in some application could be very important. And here now we see the common mode rejection ratio for the various tips, various amplifiers, and starting 160 and of course going down to lower value. This is not plus sign, not minus sign. So it's going down. And here is now the input impedance. Again, nothing special about it because the amplifier is an amplifier. I mean, there's nothing new about that. So it has the characteristic of an amplifier except for the common mode rejection ratio, because the amplifier has no connection to ground whatsoever. All the power is coming through the fiber optics, okay? So only the very minute capacitances are affecting some leakage to the ground. And we see here again the drop in the impedance. And finally, I come to the shots that I've shown earlier, the screens of the oscilloscope. And now let's understand what's going on. Okay, so we are measuring the two gates, the high side and the low side. We are measuring them with two probes, the Bumblebee and with the opto-fiber probe of Tektronix. Okay, so this is now with the Bumblebee. You see it here, and this has to be, this is the low side now, gate of the low side. And here is the opto-fiber Tektronix measuring the high side. Okay, so this is the low side, this is the high. There's nothing we can say here, but here the two are switched. So the low side now is the opto, while the high side is the Bumblebee. Okay, so now we can compare apples to apples. So let's look at the low side. The low side measured by the opto, the low side measured by the Bumblebee. Well, look at this. This is much higher than here. I don't know if this is the absolute value, absolute correct value. Also, we see here the high side. This is with the opto, and this is with the Bumblebee. You see here, much higher. So the question is, which one is correct? Because there are a couple of options here. Number one is that the Bumblebee has a much wider bandwidth, and consequently, this signal is correct because the Bumblebee is capable of replicating it, while the opto-fiber is sort of smearing it out. On the other hand, it could be that the Bumblebee is actually adding some oscillation or enhancing some of oscillation, which here we don't see them at all. Okay, so there are these two options that one has to consider. I'm not going into it. This is just a food for thought. You see here that two high-end probe, probably the best probe available today, are showing different results. Now this is now a GaN transistor. It's a fast switching. You see this is 120 nanosecond per large division here. You see this is the midpoint over here, and you see that this midpoint is switching, like the full time here, is probably in the range of 5 nanoseconds or something like that, or 6 nanoseconds, and this is for a span of 400 volt, okay? So we are talking about So we are talking about something like 60 volt per nanosecond change here. So these are very fast switching signals. And also these oscillations are in the range of 100 to 150 megahertz. We're talking about very high frequencies here, which you'll find in the GaN transistor, very typical. So measuring them and understanding them is exceptionally important, and probably you like to use the best probes available, but here you have two probes, very good ones, which are showing different results. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you find it of interest, and perhaps it will be useful to you in the future. Thank you very much.